What's up, everybody? Welcome to Geology. So, if I were to ask you right now, think in your head, how did the Earth form? What's your answer? And I'd be willing to bet among the 70 something people that are in the room, right? Watching this video, somebody's going to say Big Bang. It's a big misconception, something that just like naturally, it just kind of pops in your head like that's what I'm going to say, right? What we got to realize is that there's a tremendous difference between the Big Bang and the events that formed our Earth and solar system. Big Bang, and this is just Google Images, right? Here's all the diagrams you might see for it. There's all kinds of them out there. I chose that one. Big Bang would be a thing that happened 13.7, 13.8 billion years ago. Our planet formed about 4.5 billion years ago. So run some numbers quick in your head. There's a large gap in time between this Big Bang thing and what formed our solar system much later on. This event would be the thing that gave us our universe, the whole thing. Bits flying all over the place. This is complicated. In fact, I pulled the text up. Loosely, what we're doing today is chapter 2 in your book, if you want to check that out. And not all of it. I'm going to tell you some of it we're going to skip for this course. If you were to consider the nitty gritty of that in an astronomy course, it's complicated. There's a lot to it, right? We're going to say, cool, it happened. And it happened about 13.8 billion years ago. That gave us the whole entire universe. Stuff's everywhere now, for lack of a better word. And some of that stuff would eventually turn into what we call Earth and Kevin and coffee mugs, whatever it may be, right? That had to come from somewhere. The Big Bang gave us the container, the whole entire thing. You'll see it sometimes referred to as an explosion. In fact, I think it's in our Earth Science State Standards. It's a terrible term for it. There's no like, it's not like watching an explosion on TV. There's no big ball of flame. It's different than that. It was a very rapid expansion of matter from an unimaginably tiny point, spreading out, cooling, and in fact still cooling and spreading. And that's where I'm going to say, let's pump the brakes a little bit on it. If you check out this section of the book, this is the PDF version, by the way. If you do like the online version, it looks a little different, but it's identical. We're going to say, yeah, Big Bang, cool. I'm going to probably pass on some of the astronomy stuff, though, because we're in a geology course. This is done pretty well. I don't mind it. Check it out. But it's not going to be something I'm going to pop onto your tests or quizzes for information's sake. Until we get a little closer to forming our planet, because that's what we're here to talk about, geology, right? So out of all of the bits that are flying around, stars form, compress. They're powered by a thing called fusion, where atoms are smushed together into a larger atom, and this releases energy with some physics that we're not going to figure out right now, and eventually burn through it like a fuel, although burning a fuel is not at all the right way to do it. To think about it, it's a good example because we've all done it, right? You've got a tank full of gas, you run it until it's empty. Conceptually, that's kind of how it works. Stars have a finite amount of this that they can fuse, and then they can start fusing the larger ones too, but there's an end game, and eventually they're going to let all their contents go. It's going to be the end game for our star too, the sun. It's all over at that point. Our sun should last about, 9-10 billion years, so we're like maybe halfway-ish through our star's life cycle. And when it changes, it's, and the whole entire solar system is going to be toast. It's gone, But those bits may fly off and form other things at some point. And that's what this shirt and this face is the little bits that were in stars at other points, bits of the universe that compressed and created these atoms that make up this screen and everything you're looking at, right? And that's kind of, I guess, what the geology thing is going to be, is how did we take all of those bits and form this planet, and then take this planet and figure out how to use its resources to make things like phones, whatever. All right, so let's get at it. So if we've got these big clouds, nebula is going to be the term for that. Note that one. I bet that's going to be on the quiz at some point. Would be this like interstellar cloud of gas and dust floating around, and as things get closer to each other, whether it be because of static electricity, whether it be because once things get larger, they have gravity. we should mention gravity quick. I did not pull that up. There's going to be plenty of a yep. So the force of gravity, and you can go and argue this with physicists too, but this is the basic Newtonian version of it, which says that force of gravity is equal to this a number g, a gravitational constant. It's just a number. Don't worry about it. Times the mass of two objects divided by the distance between them squared. So if you take two objects, these two pencils have a gravitational force between them. This has a mass. This has a mass. They're yay far apart. There's a very small force of gravity that's going to want to pull them together. Now, the strength of my hands, the strength of the gravity of the planet pulling them that way is way, way, way more, but it's there. So if we are in this area and we've got no other forces really there, and bits start to get a little bit bigger, they can pull more bits towards them. And then that bit's bigger, which means it has a bigger force of gravity, which means that it pulls more bits towards it, which means that it's bigger, which means that it has more gravity, which means that it pulls more bits towards it, and that continues and continues and continues until things start to contract, get more dense. Conservation of angular momentum, don't worry about that, makes things start to spin. Towards the middle is going to be where we're from the star. That's a really critical part. Like, yeah, we're here for geology. That's what we're focusing on, but that star is going to be a big thing too. Once that got big enough to begin fusion is really when we would say our solar system was born. And around that, this accretionary disk, I've heard it called a protoplanetary disk. A protoplanet is like an early form of a planet. Like a prototype for a car is an early form of a car. Protoplanet would be an early form of a planet, right? As they kind of do the same thing. There's bits in there and they get bigger and bigger and bigger, and as they spin. This textbook, brilliant. I love this section right here. This is better than any I've ever seen. If you look up the section here, if you have the PDF version, it starts on page 9. Rules of the accretion game. I love it. Check this out and read it, because it's pretty hard to imagine that, okay, I mean, what if it goes too fast? If it goes too fast, it's going to fling away. What if it goes too slow? If it goes too slow, it's going to get sucked into the sun. Like, you ever do that thing where you put the quarter in and it spins around one of those things? You know what I mean? It has to have just the right ingredients to keep it going in orbit. And it's been in orbit for 4.5 billion years, right? Along with all the other planets. But it's a very delicate balance. And during that time too, yeah, there's things hitting the planet all over the place. It's a very violent time in Earth's history. Hades. Think of that like a hell-like time on Earth. I pulled up Mustafar here for the Star Wars people out there. This in my head, it's always been like, yeah, whoever designed this saw like diagrams of the early Earth and kind of based it on that. This hardcore Star Wars geeky website I got it off says Mustafar used to be green and lush. So apparently, lore-wise, it's not accurate. But I think in terms of what they rendered here, it'd be kind of like this. It'd be a very nasty place. I'd have to picture more impacts coming in and a really thin crust, and you don't get Darth Vader's castle either, but it'd be that kind of situation very early in Earth's history. Violent, constant impacts, because we still have in this accretionary disk, this protoplanetary disk, a lot of stuff flowing around. And it would just be a lot of time and a lot of orbits until all that stuff got either sucked into the sun, flung far out, pulled into its own individual planets or moons, or part of the asteroid belt. The asteroid belt's kind of neat because it might be kind of like what it was like just before we formed the planets. And from what I remember, again, this isn't an astronomy course, it has something to do with being right next to the largest planet in the solar system, that the gravity from that monkeys with that orbit enough that it doesn't allow it to form a planet as the other 8 did. The other 8 planets plus all the other planets like Pluto and its friends that are way out there. So run that forward in time enough collisions, and you're going to end up with a nice, clean, neat solar system. Obviously, there's still some stuff floating around. You get meteor showers, that's a sign of running into things. Ask the dinosaurs, they had a run-in with a meteor that didn't go so well. There's still things out there, but I'd say for the most part, it's been a pretty stable, clean environment to form a long-term planet on, right? Probably happening in other places in the universe, though pretty far out. And it is a very delicate balance, right? Earth is in a very ideal spot, close enough to the sun being the right size. I should just say a star, right? Close enough to a star that's the right size. To have the right temperatures, the right combinations of water and rock and all of that for life. That collision that resulted in the moon, we have a we don't have a large moon strictly. We have a large moon relative to the size of our planet. You know what I mean? Maybe I didn't say that right. Like there's bigger moons all over the place, but the size of our planet compared to the size of our moon, we've got a pretty big moon. And that does a pretty good job as it goes around us of like keeping us stable. The way the Earth is like a top and it wants to wobble around a little bit, that helps us a little bit more stable. Life, the evolution of life, really likes that stability. So are there other ones out there? Likely, but at outrageous distances. Once you start to think about these distances, it's inconceivable. It's out there. I don't want to go too far out there. Let's stick with geology, right? So where we got to go, this is going to come close to wrapping it up for today. Where we got to go with this is, okay, if we went from this Mustafar system, like, and I won't put any Star Wars stuff on the test. Don't worry if you're worried about this. How do we go from this very Hadean early Earth, which we should probably like, before I get too distracted here, how do we go from this very early Earth to what we see today? And that's going to be where we start to think about tectonics and start to think about how do we get all these different layers. If we went from this big, very young, big molten mass to this idyllic place to set up life and civilization, there's obviously a lot of steps in between, right? Today, all I really want to accomplish is that formation idea from the nebula, the protoplanetary disk, from the Big Bang, and those two numbers, that 13.8-ish billion years for the planet, I'm sorry, for the universe, and 4.5 for the planet. Just to like say, hey, let's all get on the same page here. Again, chapter 2, the learning objectives that have to do with like the nitty gritty on how we know the Big Bang was a thing. I'd say that's like, read it, check it out. It's cool, but I'm not going to have it be part of this course because I want to just stick to the geology and not get into the evidence, the abundant, ample evidence we have for the Big Bang. Just an interest of time. So all of that we can probably maybe pick up around here. 2.2 is going to be how we really start to form planets and solar systems out of nebulas, like this diagram too. Dust bunnies get bigger and bigger and bigger, right? They accrete, kind of that same idea. All good stuff through here, and really like this accretion game thing is so brilliantly simple the way they explained it. I like it a lot. So check that out. Keep it up. It's been nice to see everybody in the intros. I'll keep reading those, and soon we'll get into differentiation and then how this very, very, very thin, crunchy outside became what we would consider tectonic plates, consider the place where we live, and how that affects geology and humans. Thanks, folks. We'll see you soon. Take care.